In this video, we are going to learn how to evaluate surface integrals of vector fields. Before we do that, let's talk about line integrals, and more specifically, line integrals of a vector field. So when evaluating the line integral of a vector field, the direction the curve was transversed affected the result. This meant we had to ensure our parameterization of the curve moved in the correct direction. So if we remember notation for line integral of a vector field, that was the integral along C of f dot dr. And this represented the work done by the vector field in moving an object along the curve C. And work could be positive, negative, or zero based on how we were moving along the curve in the given vector field. So that's something that we had to consider when we were creating our parameterization of the curve. So let's say we had the unit circle as our curve. We could either choose to go counterclockwise or clockwise, and that would have an effect on our answer. The equivalent of this idea for surfaces is called orientation. Orientation, which can be thought of as defining the positive side of a two-sided surface. So now, as we set up surface integrals of vector fields, we're going to have to take into consideration the orientation of each surface that we're working with. Now, how do we define orientation? So a smooth connected surface S is orientable, which means two-sided, if it is possible to define a single unit normal vector n or negative n at each point of S so that the collection of these normal vectors varies continuously over S. We orient the surface S by choosing either n or negative n for the entire surface. So essentially, pick one point on the surface. There are two choices for a unit normal vector, positive n or negative n, and they point in opposite directions. Once we've made the decision of which unit normal vector we want to use, we've made that decision for every point on the surface. And if we looked at the collection of all the unit normal vectors, we should see that generally speaking, they're pointing in the same direction. Maybe they're all pointed up off the surface. If we have a sphere, maybe all of the unit normal vectors are pointing outward, but they're all moving in the same direction with relation to the surface. The idea of varying continuously, let's suppose at one point, randomly, the unit normal vector points in a completely different direction than all of the other unit normal vectors to the surface. That would be a case where the unit normal vector is not varying continuously, and we would have an issue. So now that we understand how we are choosing to orient the surface by making that distinction of using positive or negative n, how do we find those vectors mathematically? And that's going to require a cross product that we have been using. So if we define the unit normal of a parameterized surface R of uv as either n or negative n, we compute it by finding the cross product of the partial of r with respect to u cross with the partial of r with respect to v. And since it's a unit normal vector, we need to divide by the magnitude. So this is a cross product that we have worked with in surface area when we were writing the equation of a tangent plane and surface integrals of scalar functions. And we're going to continue working with it now as we evaluate surface integrals of vector fields. Notice here we now care more about the cross product vector than the magnitude. The magnitude here is just to create a unit cross product vector or a unit normal vector. The negation of n, very simply, we just negate our cross product vector. And the reason we need to consider both of these is we don't necessarily know which one matches the orientation we need for a given surface. And really, we're just taking a guess by using this order of the cross product, partial of u cross with the partial of v. But as we learned about cross products earlier in the course, not commutative, so the order we do the cross product in matters. But nicely for us, if we choose the wrong order, we can just negate our cross product vector, and that would give us the opposite cross product. So here are some expressions that we may come across when deciding on the orientation of a surface. So upward or downward orientation, we're looking for the k component of the unit normal vector to be positive or negative for all points that we're defining on the surface. Outward or inward orientation applies only to closed surfaces, and outward orientation is defined as positive. So let's say you had a sphere. If all of the normal vectors are pointing away from the surface of the sphere, we consider that to be outward or positive orientation. And then more generally, it could just say in the direction of the positive x, y, or z axes, and the respective component of our unit normal vector should be positive for all points on the surface. Now, with that, not every surface has an orientation. The typical example is a Mobius strip, which is an example of a non-orientable surface because it only has one side. So if we trace this graph here, or at least think about tracing it, we can do our best. It's a two-dimensional graph. So start at this point, and we start moving along the surface. And then without picking up our pen, we'd then be on the inside of the surface. And then we're here, continuing along. Then I'm on the back side of this front part. Again, still haven't picked up my pen. Then I wind up over here on the back side of the surface. Keep going, all the way till we complete the trace there. And we'd be able to accomplish that without ever picking up our pen. So we started on one side, we stayed on that side, and made our way back. That is what a Mobius strip is. It's easy to create one. If you took a strip of paper, then you half turned one side, and then connected the two ends with a piece of tape, you would have a Mobius strip, and you could actually go through the process of tracing it out like we just did in our notes, but in a three-dimensional case, and it would probably make a little bit more sense. The reason why we can't orient a one-sided surface is, let's say at this point we decide that's the normal vector. Then remember, we're on the same side of the surface, so at this point the normal vector would go in that direction. And generally speaking, those vectors don't go in the same direction, even though we're on the same side of the surface. So that's where the issue would arise. Luckily for us, we are only going to deal with orientable surfaces, or surfaces that have two sides to them. But just to show you, not every surface can be oriented. So let's do our first orientation problem. Determine if the unit normal vector defines the outward or inward orientation of the sphere x squared plus y squared plus z squared equals 4. Okay, not going to use u and v. Let's use theta and phi to parameterize the sphere. So we have r of theta and phi. So that's going to be 2 sine phi cos theta, 2 sine phi sine theta, and 2 cosine phi. Now, when we have parameterized the sphere for our surface integrals of scalar functions or surface area, we didn't actually have to go through the cross product because we knew the magnitude of the cross product was just 4 sine phi, or the radius squared sine phi. But here, we need the actual cross product vector, so we have to do the work. So we're going to cross the partial of r with respect to theta with the partial of r with respect to phi. Just to save us some time and effort, let's find those partials as we set up the matrix. Give yourself some space because these tangent vectors are going to have some long components to them. All right, so differentiate with respect to theta first. So that's going to be negative 2 sine phi sine theta, 2 sine phi cos theta, 0. And then with respect to phi, differentiating, we get 2 cosine phi cosine theta, 2 cosine phi sine theta, and negative 2 sine phi. So now we have to compute the cross product. So we get negative 4 sine squared phi cos theta minus 0. Then we get 4 sine squared phi sine theta minus 0. But remember, the j component is negative when we go cofactor expansion. It's negative 4 sine squared phi sine theta. And then we get negative 4 sine phi cos phi sine squared theta minus 4 sine phi cos squared theta. We can factor out a negative 4 sine phi cos phi. That would leave us with sine squared plus cos squared, which is 1. So won't write that. We'll just cap it off there. So there's our cross product vector. We need the unit normal vector, so we have to divide by the magnitude. But as I was speaking about earlier, we know the magnitude of this cross product is 4 sine phi. So then the unit normal vector, n, is going to be, so divide the cross product by the magnitude. So we're going to get negative sine phi cos theta, negative sine phi sine theta, and negative cosine phi. So now as far as deciding if this vector is going to point inward or outward, a good way to tell is plug in a few values of theta and phi and see which direction the vectors would point. So for instance, let's make both pi over 4. We don't really care about value, we care about sign. So sine and cosine of pi over 4 would both be positive, so this I component would be negative. The j component would also be negative. The k component would also be negative. So at the point where both theta and phi are pi over 4, we have a vector with 3 negative components. So that vector would be pointing in towards the origin. And you can go through a couple of other different combinations of theta and phi, you would find the same. So this vector points inward, and we can say negative components, just so we know why we made that decision. So if we're evaluating a problem and it says across the surface of a sphere with inward orientation, well, this would be our unit normal vector. So now that we've defined orientation, let's start to build up into the surface integral of a vector field. And the way we're going to do that is defining what it actually represents. So the surface integral of a vector field can be used to compute flux, which is the amount of field passing through a surface per unit time. Often we think about this field representing the flow of a fluid. For most of us, that's a tangible example. And let's say the surface is a screen, so we're thinking about how the fluid flows through a screen. We pause it at a moment in time, and we're trying to see the amount of that fluid going through the screen at that moment of time. Could be an electric field, could be a magnetic field. The field could represent wind. There are plenty of applications, but fluid is often the one that we go to. For this reason, we often refer to these integrals as flux integrals. So you may see it written as the surface integral of a vector field. You also might see the direction say, evaluate the following flux integral. It means the same thing. But we're going to use this idea of flux to actually develop the integral itself. So we're in 3 space, we need a surface. So we'll just draw a simple surface in. So there's our surface S. We have a vector field that's going to be moving through the surface, and it goes all the way there. So that's the vector field F. So basically, if we pause it at this moment in time, we want to know how much of the vector field is moving through this surface S. Well, how are we going to do that? Well, first we need an orientation of the surface, because we want to know, are we counting how much is going up through the surface or going down through the surface? Because that's going to be very different. One's going to be positive, one's going to be negative. So we need to orient the surface with some unit normal vectors. So what we'll do is let's divide up the surface into small regions. Remember, these are meant to be infinitesimally small, but for our drawing, we can just draw them so that they have some size to them. So within each of these infinitesimally small regions, there's going to be a point which has a unit normal vector. So normal to the surface. And we'll choose, in this case, to orient our surface upward. Right, so here we're assuming upward orientation. Okay, so if we want to compute how much of the vector F is passing upward through the surface, we really want to know how much of this vector is in the direction of the unit normal vector, which is nothing more than a scalar projection of vectors. Right? So we basically want to know what is the length of that shadow. And we accomplish that the same way we did for the line integral of vector fields with a dot product. So we're going to dot the vector of the vector field with the unit normal vector at the point. So this is going to be, I'll use this one, F dotted with N. And we want to compute that at all of these infinitesimally small points, which have a surface area of ds. So that's where the integration comes up, right? Summing up all of these infinitesimally small regions of surface area ds. We're going to sum up that dot product computation. Okay, so to compute this double integral over the surface of the scalar projection f dotted with n ds. Now, it's really nice to write it this way, but not very practical to evaluate it this way. So let's start to put in some other pieces. So we can replace n with the cross product definition we had. So r partial of r with respect to u cross with the partial of r with respect to v over the magnitude of that cross product. Now, if we think back to evaluating scalar surface integrals, ds was replaced with the magnitude of that cross product as well. And that was dA over some region D. So this is our unit normal vector. This is ds. We get some nice simplification here. The magnitudes cross out, and that's just going to leave us with the double integral over the region D of f dot the cross product dA. And this is more practical for actually evaluating out the surface integral of a vector field. Now, notationally, just like we had the integral of f dot dr, it was a really nice compact way to express the line integral of a vector field. We're going to define n ds as ds, where s is a vector, and that's just going to be a really nice compact way to express a flux integral, or surface integral of a vector field. So let's formally define everything. So let S be an oriented parametric surface on domain D with orientation determined by the unit normal vector n. If the vector field f is a continuous vector field, then the surface integral of f over s, or flux of f through s, is given by, so there you can see that nice notation, double integral over the surface s of f dot ds, where s is a vector now. Okay, so make sure we distinguish it between ds for a scalar surface integral. And then what we showed is that's really evaluating the dot product of f with the unit normal vector, ds. Okay, you can also see it expressed this way. And as far as evaluating, we want to redefine the vector field in terms of u and v, dot that with plus or minus the cross product of the partial with respect to u and the partial with respect to v, dA. Now, we didn't write the plus or minus in the previous example because we assumed upward orientation and we were just kind of deriving it, but we're going to make that choice. Choose based on orientation. All right, so you're going to choose to use the positive or negative cross product vector based on the orientation of the surface. Define the vector field in terms of u and v, compute the dot product, and then we're back to evaluating a double integral. Okay. If the surface is defined explicitly as z equals g of xy, we can take a bit of a shortcut. So this is basically a trivial parameterization. If your surface can be defined with a trivial parameterization, then here's what we're going to be able to do. We're going to be able to go up a dimension and define a new function, capital G, which is, let's say, z minus g of xy, where one of the level surfaces of this function one dimension higher is the same as the surface z equals g of xy. And why is this relevant? Well, if this sounds familiar, it is. This is how we wrote tangent planes, where we used the gradient vector. So if our surface can be defined trivially, then we can define this function one dimension higher, find the gradient of that function. So negative partial with respect to x, negative partial with respect to y, 1. The magnitude of that gradient would be the square root of, I'll drop the negative since we're squaring, but partial with respect to x squared, partial with respect to y squared, plus 1 squared, which was the exact expression that we used for the magnitude of the cross product. Oh, that's on the last slide. I thought it was up there. Was the magnitude of the cross product when we were doing a scalar surface integral. Okay, so in the case of a trivial parameterization, we can then rewrite this integral as a double integral over the region D, redefine the vector field in terms of only x's and y's, so replace z with whatever function it's equal to, dotted with plus or minus the gradient of g, still need to make that choice based on the orientation, and then dA, right? Notice the magnitude of the gradient doesn't show up in the double integral because it simplified with the magnitude of the gradient, that same expression that would be there replacing the ds term like we did on the previous slide. Okay, this only works for a trivially defined surface, right? So if you were going to do it parametrically as a trivial parameterization, we can save ourselves some time and effort. So we've built up a lot, now let's actually do some problems. So evaluate the double integral over the surface S, where the vector field is e to the xy, 1 e to the z, and S is the cylinder parameterized by r of uv, u, 9 minus v squared v, u is bound from 0 to 4, v is bound from 0 to 1, oriented in the direction of the positive y-axis. Okay, a lot of information is given to us when we were evaluating these flux integrals, or these surface integrals of vector fields. So first thing, let's find our normal vector to see if it matches the orientation we're looking for. So we're going to cross the partial of r with respect to u and the partial of r with respect to v. Again, we just make that assumption and we make adjustments if it's not pointing in the right direction. So partial with respect to u is 1, 0, 0. With respect to v is 0, negative 2v, 1. So our cross product vector 0 minus 0 is 0. 1 minus 0, but j is negative, so negative 1. Negative 2v minus 0, negative 2v. Okay, so now we have a cross product vector, we have a normal vector, but we need to check if it goes in the positive y direction. So we look at the j component of the vector. Negative j component doesn't point in the right direction. So then we're going to use the negation of the cross product vector, which is going to be 0, 1, 2v. Okay, basically what that means is we should have done the cross product in the other order. We didn't know that ahead of time, so we just make the adjustment, negate the cross product vector, and keep moving. Then we need to redefine the vector field in terms of u and v. So that's going to be e to the u times 9 minus v squared, 1, and e to the v. Now we dot the vector field in terms of u and v with the correct normal vector. So we have the double integral of that dot product, so that's going to be 0 plus 1 plus 2v e to the v, and we can go du dv. U goes from 0 to 4, v goes from 0 to 1. Now I'm going to skip all the integration in this video. We've done so much integration, you can look back to other videos. This one in particular would require an integration by parts, so always great to practice, but you're going to get 12. For me, the focus of this video is more on the setup, the orientation, the cross product, doing the dot product to set up our double integral over the actual integration. But again, great practice. Evaluate the double integral over the surface S of f dot ds, where the vector field f is 2zyx, and S is the part of the plane x plus y plus 2z equals 2 in the first octant with upward orientation. Okay, so this is definitely a surface that a trivial parameterization would make sense for. And if we were going to do a trivial parameterization, we would solve for z, so 2 minus x minus y over 2. Right? So could we do this parametrically? 100%. X, y, 2 minus x minus y over 2 would be our parameterization. We can find our two tangent vectors, take their cross product. That is 100% a great way to do it. But let's do this example by skipping the actual cross product. So since we could use a trivial parameterization here, we can define a function one dimension higher. So we need to move all the terms to one side. If you pay attention, it's upward orientation. That means we'd want a positive z component. So if we could keep z positive, that would just be helpful. But if we don't, honestly, it's easy enough to adjust. So I'm going to move all the terms to the left side. So that's going to be z. I'm going to simplify minus 1 plus x over 2 plus y over 2. Then the gradient of g then is 1 half, 1 half, 1. Check upward orientation. Look at your k component. Okay, this is upward. Check. It's always good to check yourself there. Then we need to redefine the vector field in terms of x's and y's only. So that's going to be 2 times this, which is just 2 minus x minus y, and then yx. So then we're going to have the double integral of the dot product of the vector field with the normal vector. So that's going to be 1 minus x over 2 minus y over 2 plus y over 2 plus x. We need to figure out the region we're integrating over. So it does say that we're in the first octant, and we define everything in terms of x's and y's. So let's just look at the xy plane here. Z is 0, so then we'd have 2, 2. There's our region D, y equals 2 minus x. We could go type 1 or type 2 here. Let's just keep it simple. We'll go type 1 for that region in the xy plane. That means dy dx. So 0 to 2 minus x, 0 to 2. So we can clean up, well, at least clean up the inside. So 0 to 2. That's going to be 1 plus x over 2 dy dx. And again, if you integrate everything out for practice, you're going to get 8/3. So this is our example of a surface that could have been parameterized trivially, where we can avoid the cross product by finding the gradient of the vector, the gradient of the function g that we defined. Now let's bring that sphere back in. So evaluate the double integral of f dot ds, where the vector field is y negative x1, and s is the sphere x squared plus y squared plus z squared equals 4 with outward orientation. So this is one we'd want to parameterize. So I know we did it earlier, but let's just get that parameterization written down again. So that's 2 sine phi cos theta, 2 sine phi sine theta, and 2 cosine phi. Since we are going to integrate here and we have the whole sphere, let's put some bounds in place. So theta is going to be bound from 0 to 2 pi, and phi is going to be bound from 0 to pi. Now, we did the cross product earlier. We went a little bit further than we needed to go because we found the unit normal vector. But then once we started our derivation, what I want you to notice is we didn't actually need the unit normal vector, we just needed the normal vector. So I'm going to go up a few steps if you're looking back at that slide. So just looking at the cross product of theta and phi, and actually looking back, that was inward orientation, but we want outward. So let's negate this vector. If I can squeeze it in there. Let's negate that vector. So the negation of that cross product vector is going to be 4 sine squared phi cos theta, 4 sine squared phi sine theta, and 4 sine phi cosine phi. Okay, so this is going to be outward, right? And I like just writing it outward, check. Okay, so we have an outward pointing normal vector by negating the cross product. Again, if we didn't have this cross product done already, we would do the cross product out. We would check. In this case, we would have negative components, and then we'd have to realize we'd have to negate it to match the orientation of the surface. Next, we need to redefine the vector field in terms of theta and phi, our parameters. So that's going to be 2 sine phi sine theta, negative 2 sine phi cos theta, and 1. Okay, now dot the normal vector with the reparameterized vector field. So we're going to get 8 sine cubed phi sine theta cos theta minus 8 sine cubed phi sine theta cos theta plus 4 sine phi cosine phi d theta d phi. Theta goes 0 to 2 pi, phi goes 0 to pi. We get some nice simplification in here. This is going to then simplify to be the integral from 0 to 2 pi, 0 to pi of 4 sine phi cos phi d theta d phi. And if you practice your integration out here, you're going to get 0. So these problems take a bit of work. We skipped the integration step for all three examples, so that would even make these a bit longer than what we have already done. But the key here is remembering the process. We need to find a normal vector that we can define the surface's orientation with. We use the cross product or the gradient for the trivial parameterization. We need to redefine the vector field. Then we dot those two vectors together, set up the double integral, and integrate. So similar steps to the line integral of a vector field, where we're doing the vector field dotted with r prime, but here it takes a little bit more work to find that normal vector. In this case, the sphere was a closed surface, and one of the theorems that we are going to cover in a coming video is going to give us a simpler way to compute the flux through a closed surface. But we're not there yet. Let's practice with this method, and I'll see you in the next video.